High above Earth's cerulean swirl, an astronaut glides from the airlock of the International Space Station. She lets go of the handrail, and for a heartbeat, appears perfectly still, a lone figure, afloat in velvet silence. Yet without firing a single thruster, she is hurtling around the planet at 7.7 kilometers per second, surfing a curve of spacetime that never ends. Motion, it seems, does not wait for engines. It is stitched into the fabric beneath her gloves. The illusion of rest has always tempted us. Set a teacup on the table, and it stays put. Step off a moving boat, and the pier feels solid, dependable. But history whispers a different story. Galileo watched lanterns, top Tuscan ships, and realized the deck was no privileged stage. Newton chiseled that insight into law, declaring that a body in motion will carry on no coaxing. No cause unless another body intervenes. Inertia, he called it. The quiet sovereignty of straight-line movement. Yet straight lines are rarer than we imagine. The deck rolls with the tides of Earth's spin. The planet loops the sun. Sun pirouettes around the Milky Way. The galaxy itself is dragged by unseen currents toward the great cosmic cities of Virgo and Laniakea. We dwell on a spiral staircase of velocities, each step hidden under the carpet of daily life. Lift your gaze farther still, and a grander restlessness appears. Edwin Hubble noticed galaxies slipping away from one another like glowing embers cast into the dark. Today we map that flight in exquisite detail, and the data reveal a deeper puzzle. The cosmic expansion is speeding up, as though a subtle hand, dark energy we name it, were tugging on every meter of space. In such a universe, what does at rest even mean? Can inertia coexist with a stage that stretches beneath the actor's feet? Some thinkers, like Ernst Mach, wondered whether motion is defined only by the whole. Perhaps the mass of distant galaxies whispers to every atom, telling it what counts as straight, what counts as still. Einstein absorbed that hint and found that free fall is not the absence of gravity, but the purest expression of inertia. Objects following the natural curves of space-time itself. On this view, the astronaut, the teacup, and a drifting comet share the same calling. To trace Geodesics lines so honest, they need no push. And yet, an unsettled note lingers. Space is expanding. If the very ruler we measure motion with is changing length, then inertia is no longer merely a law of persistence. It becomes a conversation between matter and metric, between the stubbornness of mass and the pliability of the cosmos. That is the journey before us. We will step from Newton's quiet revolution to Einstein's soaring geometry. From the whispered pull of dark energy to the fate of Voyagers coasting into an ever lonelier sky. Along the way, we will ask a deceptively simple question. Why does anything move at all, and why does nothing, not even stillness, ever truly last? Imagine you are sealed below deck on a calm-bellied galleon. No porthole, no roll of horizon. Only the lantern's meek glow and the creak of timbers. A glass of wine rests on the table. Beside it, a brass ball lies ready on a gently sloped wooden plank. You release the ball, rolls, slows, and settles. You tilt the plank again. And again the ball obeys exactly as it would in any motionless cellar ashore. Galileo loved this cabin thought experiment, for it whispered a quiet heresy. The ship may be slicing through waves at 10 knots, yet the laws inside neither feel nor care. Motion, he intuited, is not something you carry like luggage. It is a condition that, once acquired, demands no further tribute. The candle's flame stands upright not because the vessel is truly still, but because every particle of flame, glass, and air shares the ship's invisible glide. From this humblest of stages, the cramped hold of a Renaissance vessel emerged a revolution. If experiments cannot reveal steady motion, then rest and uniform travel must be twins wearing different costumes. The sea, Galileo realized, exposed a flaw in centuries of Aristotelian certainty. Perhaps nature does not crave stillness at all. Perhaps left unbothered, motion would simply be a silent companion, needing no cause, awaiting only recognition. 4 decades later, in a drafty Cambridge study, Isaac Newton set quill to parchment and gave Galileo's intuition the weight of law. First principle, every body perseveres in its state of rest, or of uniform motion in a straight line, unless compelled to change that state by forces impressed upon it. 20 Welsh words in Latin dress, yet they dethroned to millennia of common sense. Aristotle had taught that a cart rumbles only while the horse strains, that an arrow keeps flying because the air itself continues to push it along. Newton answered with radical economy. Remove friction, silence the wind, and the cart will glide forever. Strip the arrow of drag, and it will wander endlessly among the stars. Force, he said, is not the sustainer of motion, but the author of change in motion. An editor's pen, not the page beneath. To his peers, the claim felt perilous. After all, earthly experience teems with slowing wheels and falling arrows. But Newton had seen deeper. Those stoppages arise from hidden pushes. Gravel under a wheel, air against a shaft. Not from any natural longing for rest. Between pushes, the universe is content to let momentum stream onward, pristine and unburdened. Thus, inertia became more than a property. It became a promise. It states that the cosmos keeps immaculate bookkeeping. Whatever straight-line motion an object possesses, it owns outright, untaxed by time. Only an external nudge, a force, can renegotiate that ledger. In this single stroke, Newton transformed motion from fleeting gift into enduring right, granted to every planet, pebble, and drifting human heart. On a summer evening in Woolsthorpe, Newton filled a wooden pail, hung it by a rope, and set it spinning. At first, the water's surface stayed calm, while the bucket blurred around it. Then, as the liquid caught the rotation, its surface climbed the walls, forming a quiet parabola. When Newton halted the bucket, the water continued to whirl, the curved surface lingering until friction bled the motion away. To Newton, this modest experiment spoke volumes. The creeping rise of water could not be blamed on the bucket's boards. They had briefly rested while the water still spun, so the cause, he reasoned, must be rotation with respect to something else, something unseen yet universal. He called it absolute space, an invisible scaffold against which true motion and true stillness are measured. This idea granted inertia a silent referee. Stone tied to a sling tugs outward not because it senses the twine, but because its straight-line instinct clashes with a forced circle around that immaterial stage. Even if every star vanished from the sky, Newton believed the stone would still feel the pull. Absolute space needed no landmarks. Yet a seed of doubt lay dormant in the bucket's swirl. If forces arise only from motion relative to this undefined backdrop, might that backdrop itself be nothing more than the distant mass of the universe? Einstein would later wonder. Mach before him would prod. But for a century and more, Newton's unseen lattice of space remained the quiet canvas upon which all celestial choreography was drawn. Paris, 1851. In the vaulted dome of the Pantheon. Leon Foucault releases a 28-kilogram brass bob suspended on a 67-meter wire. With each languid swing, the pendulum traces a line in sand, and hour by hour that line slowly rotates beneath the tourist's feet. The floor, the pillars, the city itself are turning. The pendulum is merely keeping faith with inertia, pointing toward a frame beyond the rattling carriages of the Champs-Élysées. Half a world away, trade winds curve and hurricanes spin, sculpted by the same invisible hand. The Coriolis force no force at all, merely inertia misread from a rotating deck, twists air and sea into vast spirals. Stand in the eye of a cyclone, and you feel nothing push you sideways. Yet the storm's arms curl because Earth pirouettes beneath them. These phenomena reveal motion without a single mile walked. They show that to detect rotation you need only watch how inertia expresses itself. A pendulum that refuses to follow the floor. Water that heaps against a bucket's rim, clouds that trace planetary whirls. No anchor is necessary, no celestial compass. Only the steadfast straightness objects cling to unless compelled. Such experiments whisper a radical message. Inertial frames are not bestowed by gilded labels like at rest or in motion. They emerge from relationships between swinging pendulum and turning Earth, between spiraling storm and spinning globe. The stage feels less like Newton's absolute void and more like a dialogue with the cosmos itself. A dialogue that will grow louder when Mach and Einstein ask whether the distant stars might be answering back. By the late 1800s, physics had grown almost smug. Newton's mechanics charted planets with clockmaker grace. Maxwell's equations revealed light as a trembling electromagnetic wave. Waves everyone knew need a medium: water for ripples, air for sound. So scientists conjured an all-pervading luminiferous ether, an intangible sea through which light must sail. Surely if Earth coasted through that sea, a sensitive instrument could feel the headwind. Enter Albert Michelson and Edward Morley. In a quiet Cleveland basement, they floated an interferometer on a pool of mercury, splitting a beam of light into two perpendicular paths. If ether existed, turning the apparatus should stretch one light path, compress the other, and shift the interference fringes like ripples in a pond. They waited. The fringes held fast, no drift, no sigh of cosmic breeze. They turned the granite block again, and again silence. The null result rang louder than any positive finding. Either Earth always sits uniquely still in the ether, an implausible cosmic vanity, or the ether itself is a fiction. More unsettling, the speed of light appeared steadfast, immune to the motion of both source and observer. Here, inertia met something stranger than frictionless ice, a signal that refused to add or subtract velocities. A law unwilling to bend for common sense. The cracks spread quickly. If light needs no medium and no preferred frame, perhaps no such frame exists at all. Into that widening fissure, a young patent clerk named Einstein would step. Armed with the audacious idea that the straightest possible line in the universe may be drawn not through space alone, but through space-time itself. We have followed inertia from Galileo's hidden cabin to Newton's spinning bucket, from Foucault's solemn pendulum to Michelson's stubborn light. Each experiment has pulled another rug from beneath the notion of an absolute backdrop. Motion, we have learned, is not a privilege granted by a cosmic stagehand. It is the native state of things. And stillness, more often than not, is merely motion we share. Yet questions gather like clouds at twilight. If no lantern marks an ultimate rest frame, what fixes the line that inertia calls straight? Why does a rotating bucket know it is spinning, even in an empty room? And could that knowledge, as Ernst Mach dared suggest, be whispered to it by the far-flung galaxies themselves? Might inertia be a handshake with the total mass of the universe? A silent referendum in which every star has a vote? These riddles press us to widen our lens. In the next chapter, we will leave Newton's absolute space behind and enter a realm where frames float anchorless, where the very geometry of spacetime decides what counts as a geodesic path. We will weigh Mach's provocative principle against the evidence of rotating heavens. Watch Einstein fold gravity into inertia, and glimpse how the cosmos itself may set the rules for every apple's fall and every satellite's glide. It's so let the bucket's water settle and the pendulum's sand run smooth. Ahead lies a deeper mystery. If motion is free, yet reference is relative, who or what draws the grid that guides the stars? Step aboard a Japanese Shinkansen, slicing through countryside at 300 kilometers an hour. Inside the cafe car, a barista tilts a silver pitcher. The milk ribbon curls into a rosette with lazy grace, untroubled by the hurtling world beyond the window. No cup skitters, no spoon rattles against porcelain. To every traveler nursing a latte, the carriage feels as hushed as a library. Swap rails for sky. A parabolic flight aircraft, nicknamed the Vomit Comet, arcs downward, and the cabin dissolves into weightlessness. Pens float, laughter bubbles, yet a camera fixed to a seat frame sees everyone drift in slow ballet. Unaware that the aircraft itself is plunging earthward at hundreds of kilometers per hour. Now ascend to the International Space Station? Uncapped droplets coalesce. Coffee orbs glide from pouch to lips. And astronauts perform somersaults with fingertip pushes. The station circles Earth every 90 minutes. But inside, only the view through a hatch window betrays the speed. Each scene, train, plane, orbital lab, confirms a profound principle. Within a cabin moving at constant velocity, no purely internal experiment can reveal the motion. Whether you trace pendulums, pour beverages, or toss keys, the outcomes mirror those in any quiet room ashore. The universe, it seems, grants no badge for steady travel. Uniform motion is indistinguishable from rest. Inertia, once Newton's radical decree, now whispers a subtler truth. Stillness is not an absolute location, but a shared state of glide, felt only when some outside force dares to disturb the peace. Yet a nagging question lingers. If all straight-line motion is created equal, what about rotation? Spin in your desk chair, and you feel the outward tug. Spin in an empty field at midnight, and the tug persists. Against what exactly are you turning? Enter Ernst Mach, the sharp-eyed 19th century physicist-philosopher. He gazed at Newton's rotating bucket and wondered whether the water's curved surface truly testified to an invisible, absolute space. Suppose, Mach mused, the stars overhead were whisked away. Would the water still climb the bucket walls? Or does its rise depend on a dialogue with that glittering backdrop? Perhaps inertia itself, its self-resistance to spin or shove is a gentle handshake with the distant mass of the universe. The idea is disarming in its simplicity. Motion means nothing unless there is something else to move relative to. Pirouetting ice skater speeds her spin by tucking arms. But the sense of rotation? The outward pull she counteracts might be her body conversing with Andromeda and the Virgo cluster, silent partners across unfathomable gulfs. Mach's principle, as it came to be called, lacked equations, yet seated deep unease in young Albert Einstein. If inertia is woven with cosmic matter, then perhaps gravity and motion are threads of the same fabric. Einstein carried that hunch into his happiest thought, the elevator paradox that would birth general relativity. For now, let Mach's whisper echo. The straight lines and steady spins we take for granted may be votes tallied by every star in the night sky. Our next step is into an elevator, where floors vanish and space itself reveals how profoundly that cosmic quorum shapes the paths we call inertial. Picture yourself in a windowless elevator adrift in deep space. The cabin floats weightless. Your feet hover just above the floor. Now imagine an unseen hand attaching a cable and hauling the car upward with constant acceleration. Instantly, your soles press against the metal, coins fall to the deck, and a dangling keychain points down. From inside, no experiment can tell whether a planet's gravity tugs at you or the cable's steady pull fakes it. In 1907, this simple daydream washed over Albert Einstein like sunrise. The happiest thought of my life, he called it. Gravity and acceleration are locally indistinguishable. Extend that idea, and inertia itself, once a silent companion, becomes the star of the show. A falling apple is not pulled. It is freely tracing the straightest possible line through curved space-time. An unforced geodesic. You, standing on Earth's surface, feel weight precisely because the ground accelerates upward, forever deflecting you from that effortless path. Experiments now enact Einstein's reverie with exquisite precision. Atomic fountains toss clouds of rubidium upward. As the atoms rise and fall, they tick like quantum pendulums, measuring tiny frequency shifts predicted by the equivalence principle. Laser interferometers compare clocks on airplane wings to those on runways, confirming that acceleration and gravity trade roles flawlessly. Thus, inertia is reborn as geometry. The elevator's floor, the Earth's crust, even the bright arc of Mercury's orbit. All are stage props that push against objects, yearning to glide straight on space-time's subtle curves. If space-time itself sets the rails of inertia, can we see those rails twist? Engineers answer with gyroscopes, stalwart guardians of direction. On jetliners, ring laser gyros trap light racing in opposite loops. Any rotation lengthens one path, shortens the other. And the interference whisper tells pilots their true heading, indifferent to clouds or compass errors. Push the concept to cosmic scales, and you find Gravity Probe B, launched in 2004. Inside its dew-cold shell floated for quartz spheres, polished rounder than raindrops. Each sphere spun like a perfect top, its axis pointing at a distant guide star. According to Einstein, Earth's mass dense space-time, and because our planet also turns, drags space-time around with it in a gentle whirl. After a year of orbit, the probe reported a minute drift, just 39 milliseconds, but exactly the swirl general relativity foretold. The gyroscopes had felt space-time's eddy without touching air, water, or magnetic field. Closer to home, consider a spinning bicycle wheel held by its axle. Tilt the axle and mysterious torques appear, steering it against your hands. Yet those torques vanish inside free-falling parabolic aircraft. The wheel's axis keeps faith with distant quasars, defying the plane's fleeting arcs. Even a child's toy becomes a cosmic compass, once divorced from friction and floorboards. These experiments reveal a universe where rotation is never absolute, yet never free. It references space-time's local twist, which in turn is sculpted by the mass and motion of everything else. Mach's whisper lingers, now spoken through cryogenic tops and loops of captive light. The cosmos is both stage and choreographer, guiding every pirouette by the weight of its own invisible hands. Stand in a quiet desert and point a radio dish at the sky. Bathed in microwave haze, the afterglow of the Big Bang, the instrument hears a faint hiss, only 3 kelvins above absolute zero. Yet that hiss is hotter in one slice of sky and colder in the opposite slice by 1 part in 1,000. The pattern is a dipole, a Doppler blush betraying that Earth. The Sun and the Milky Way surge through the cosmic sea at roughly 370 kilometers per second. Have we then rediscovered Newton's absolute rest? Not quite. The cosmic microwave background offers a practical compass, not a privileged throne. Any observer, anywhere, can subtract the dipole from her maps and call herself at rest with respect to that ancient light. The laws of physics remain unchanged. If she instead rides the galactic wind, only the temperature pattern shifts. Inertia still refuses to pick favorites. It merely notes that the newborn universe left a convenient backdrop against which we can measure our own drift. Zoom closer, and the picture complicates. The local group of galaxies clings together, ignoring the grand expansion because gravity knits it tight. Farther out, space itself stretches, carrying Virgo clusters apart like dots on an inflating balloon. Motion born not of jets or rockets, but of geometry's slow breath. Thus we inhabit nested frames. Bound orbits inside galactic eddies inside a Hubble flow. The whole flow surfing the leftover radiation of the primordial fireball. In this layered hierarchy, inertia is democratic. Straight lines are drawn locally by spacetime, while the cosmic background supplies only a gentle reference grid. A whisper, not a mandate, reminding us how swiftly our seemingly still lives rush through the deep. We have drifted from the silence of a latte on a racing train to microwaves born when atoms did not yet exist. And everywhere the verdict is the same. Motion is context, not command. Neither bucket walls nor ether winds. Not even the newborn light of the cosmos can claim ultimate authority. Instead, straightness and stillness arise from an ever-changing conversation between matter and the pliant fabric that enfolds it. But a subtler story waits in those folds. If space-time can whirl around Earth and swell between galaxies, what paths do free objects truly follow? What shape does inertia take when gravity itself is nothing more or less than geometry in motion? To answer, we must leave anchors behind and accept that the purest expression of Newton's first law is not a line on a grid, but a geodesic. The natural, effort-free trajectory inscribed by space-time's own curvature. In the next part, we will step into that geometric realm. We will ride Einstein's elevator out into interplanetary space. Feel how GPS satellites keep time by tracing geodesics bent by Earth's mass, and watch dark energy begin to tug on the grid itself, lengthening every yardstick in the cosmic loom. So pause, take a breath, and feel the floor beneath you solid, reassuring. Yet quietly accelerating upward against your innate desire to fall along an unseen curve. Ahead lies the revelation that inertia, once thought a simple stubbornness, is the universe's way of writing its deepest script. The story of how matter, light, and expanding space choreograph a dance where motion never dies, but simply follows the bends of an ever-unfolding canvas. Imagine stretching a taut silk sheet, then lowering a heavy brass orb into its center. Marbles rolled nearby trace gentle spirals toward the dip, compelled not by some hidden chord, but by the sheet's own sagging geometry. Replace silk with space-time, marbles with planets, and you hold the essence of a geodesic, the straightest path available when straightness itself is curved. Now, follow tiny Mercury, closest of the sun's attendants. For centuries, astronomers logged its orbit, expecting an ellipse that reset perfectly each lap. Yet decade by decade, the planet's closest approach, its perihelion, inched forward. As though Mercury sensed a groove in space no Newtonian map had drawn. Classical perturbations from Venus and Jupiter explained most of the drift. But 43 arc seconds per century remained untamed, a discrepancy minuscule to the human eye, colossal to the equations. Einstein's fresh mathematics closed the gap overnight. In his tapestry, Mercury is not tugged off course. It obediently follows a geodesic carved by the sun's mass, because space-time near that furnace is more steeply dimpled than Newton ever guessed. The planet's path rotates, slowly, inexorably like a clock's hand turning through cosmic noon. Extend the notion, and every falling raindrop, every drifting Voyager probe, every mote of cosmic dust is simply inertia set free, honoring the contours beneath it. Forces become reminders, nudges that something, a mountain, a rocket thrust, a photon's pressure is urging matter away from the route space-time prefers, the universe. In other words, supplies rails invisible to our senses, yet absolute in their guidance, and motion's deepest instinct is to stay on track. If space-time shapes where things go, it also shapes when events unfold. In 1962, physicists Robert Pound and Glenn Rebka perched a gamma-ray source atop Harvard's 22-meter Jefferson Tower and set a detector at the base. Photons descending the shaft gained a whisper of energy. Their wavelengths shortened because, in Einstein's universe, clocks tick faster the lower they sink in a gravitational well. The measurement, precise 2 parts in 100 trillion, proved that time is as pliable as space. 14 years later, atomic clocks boarded commercial jets. After circling the globe eastward and westward, the flying timepieces disagreed with siblings left in the lab. Mere nanoseconds adrift, yet exactly what relativity foretold once one accounted for altitude. Gravitational dilation and speed, special relativistic slowing. Our species had, for the first time, carried pocket-sized proof that time is not universal currency. It earns local interest. Today, an invisible lattice of 30-plus GPS satellites keeps your phone from wandering off cliffs. Each craft orbiting 20,000 kilometers up experiences weaker gravity and higher velocity than ground receivers. Their onboard clocks race ahead by 38 microseconds per day. Enough that, without relativistic correction, Google Maps would misplace you by 10 kilometers after a single sunrise. Engineers pre-offset the tick rate and continually tweak it, allowing geodesics both spatial and temporal to guide aircraft, farmers, and late-night pizza couriers. Thus, gravity is not a force that drags clocks, just the statement that clocks and rulers alike belong to geometry. Where space-time dips, moments lengthen. Where it stretches, seconds shrink. On this supple stage, inertia means more than moving freely. It means living in a time that is patient or hurried according to the landscape beneath your feet. On the morning of the 29th of May 1919, clouds parted over the island of Principe, just long enough for Arthur Eddington to photograph a total solar eclipse. When the plates were developed, starlight skirting the sun appeared ever so slightly displaced, bent, as if space itself wore a lens. Einstein's telegram to his mother was understated. Predictions confirmed. Yet in that shimmer of deflected photons, 2 great notions fused: inertia's straight line. Loyalty and light's own unwavering speed could coexist only if the line itself curved. A century later, the Hubble Space Telescope delights in cosmic calligraphy. Massive galaxy clusters warp space-time so deeply that distant galaxies behind them smear into Einstein rings and luminous arcs. These natural telescopes magnify objects otherwise too faint for any glass we forge, revealing infant galaxies forming just a few 100 million years after the Big Bang. Map the distorted images carefully, and an invisible scaffold emerges. Dark matter filaments outweighing luminous stars 5 to 1, yet revealed solely because light refuses to break ranks with geometry. Even solitary stars can act as magnifying glass. When a foreground star drifts across a background one, its minuscule gravity brightens the latter for days. Microlensing, offering a sensitive scale two-way exoplanets colder than Pluto. No rocket nudges these photons. They coast inertially, tracing null geodesics, whose very definition is set by spacetime's curve. Thus, every twinkle is also a testimony. Whether forming rings around clusters or whispering through solar eclipses, light evidences a truth more lasting than stone. In the universe's court, Even massless messengers must obey the contours that matter and energy script upon the cosmic parchment. Geodesics are usually serene, but let two black holes pirouette a whisper apart, and the stage itself begins to quake. Space-time ripples outward at light-speed gravitational waves, lengthening some directions while squeezing others, like a cosmic accordion. For a century, they were mathematics in search of a microphone, until the 14th of September 2015, when LIGO twin interferometers, arms for kilometers long, mirrors polished finer than starlight, heard a transient chirp. The detectors did not budge through space, rather space slid back and forth through them by a width 1/10,000th, that of a proton. A 1.3 billion-year-old black hole merger had plucked the geodesic web, and Earth resonated in reply. 2 years later, another tremor arrived, this time from colliding neutron stars. Observatories worldwide caught the afterglow, gamma rays, X-rays, even visible kilonova light seconds after LIGO's ping. Geometry had delivered both when and where the crash occurred, proving that space-time's vibrations can guide telescopes as surely as they steer falling apples, closer to home. Gentler geodesic deviation tugs twice daily at Earth's oceans. The moon and sun stretch our planet into a living hourglass. Tides lapping coastlines in rhythmic tribute to curving trajectories. On Jupiter's moon Europa, the same stretch may warm an ocean beneath ice crusts, stirring minerals that could seed alien biology. Whether they rage as black hole arias or murmur as tidal sighs, these deviations remind us that inertia is not a rigid doctrine but a dialogue. Geodesics can flex, twist, and resonate, revealing in their trembling both the hidden violence and delicate harmonies of a universe forever in motion. Imagine two starships, unpowered after launch, drifting a million light-years apart in the vast stillness between galaxies. In a universe ruled only by inertia, their separation would remain unchanged, each vessel charting its own lonely geodesic. Yet observations of distant supernova tell a different tale. Space itself is accelerating, urged outward by an enigmatic pressure we call dark energy. In this ever-swelling arena, mathematicians dub it day-sitter spacetime. Geodesics diverge exponentially, run the cosmic clock forward, and the starships watch each other fade. It's not because engines fire, but because the metric beneath their hulls stretches. Beyond roughly 16 billion light-years today and creeping closer every century, recession speed exceeds light. Beyond that event horizon, no new signal, however urgent, can ever arrive. It is not distance that dims the stars, but geometry rewriting the rules of reach. For tomorrow's interstellar navigators, accounting for that drift is as vital as Newton's gravity was to Apollo. Concepts already germinate. Autonomous craft might triangulate their position against the millisecond heartbeats of pulsars, celestial lighthouses whose rhythm factors in relativistic redshift. Deep space probes could compare laser links to remote atom clocks on Earth, updating course as dark energy expansion leans on every ruler. Even our modest Voyager 1, coasting inertially since 1989, will one day measure its speed against a cosmic background that has slipped beyond its radio whispers. Thus, the fate of motion is written not only in mass, but in the vacuum's own inscrutable script. Straight lines will forever exist, yet the canvas they cross is inflating beneath their feet, promising a solitude grander and stranger than any gravity-bound poet ever dreamed. We have followed inertia from the silk sheet swirl of Mercury to the tremor of space-time itself, and everywhere the message echoes. Motion is geometry made manifest. Freefall is loyalty to curvature. Time dilation, lensing arcs, and gravitational waves are footnotes in its flowing prose. But geometry, we now see, is not static parchment. Dark energy is quietly redrafting the grid, pushing galaxies beyond view, stretching every meter of emptiness into something more expansive than before. Where does this silent pressure come from? Is it Einstein's cosmological constant? Vacuum energy with a density that never dilutes? Or a dynamical field? Quintessence, evolving like a slow tide beneath the stars? How can nothingness possess heft? And why does its influence grow just as starlight culture arrives to notice? These riddles tug at the frontier of both observation and theory, challenging particle physics, quantum gravity, and our deepest intuitions about what a law should feel like. In the next part, Dark energy's silent push. We will chase the evidence. Type IA supernova yardsticks. Baryon acoustic ripples frozen in galaxy swarms. The subtle imprint on the cosmic microwave backgrounds, coldest hollows. We will weigh rival models, ride future telescopes like Euclid and the Vera Rubin Observatory, and glimpse how the universe's ultimate trajectory. Endless stretch, big rip, or gentle thaw, depends on the character of this most invisible actor. So steady your imagination. The stage itself is moving, and to understand motion, we must now interview the stage. An empty theater whose very planks are swelling beneath the spotlight of our curiosity. Picture distant galaxies as lanterns on a vast dark lake. In the late 1990s, two rival crews, one dubbed the Heisey Team, the other the Supernova Cosmology Project, watched for the moment a lantern flared and faded, a type IA supernova, nature's near-perfect flashbulb, because every blast releases almost the same torrent of light. Its apparent brightness tells a simple tale. How far the lantern stands and, more subtly, how swiftly the lake between us has stretched during the light's long voyage. Night after night, the astronomers sifted curves of fading starlight, fitting each with clockmaker care. The results felt wrong at first blush, too dim for their redshifts, as though the universe had spirited them farther away than expected. One data set might be blamed on dust, two on calibration, but 24 supernovas sang the same off-key note. When the numbers settled, a stunning picture emerged. Cosmic expansion is speeding up. Galaxies are not coasting inertially after the Big Bang's shove. They are accelerating, as if some gentle but inexorable pressure swells every cubic centimeter of space. In an ocean where the oars should have stilled long ago, the water itself is still rowing. The discovery appended textbooks overnight, yet its essence is beautifully humble. By timing the flicker of dying stars, we learn that the cosmos keeps pressing the accelerator silently, everywhere, all at once. Long before the first star sparked, the newborn universe pulsed like a drum. Photons and baryons light and ordinary matter locked together in a scorching plasma, sent pressure waves racing outward at half the speed of light. For 380,000 years, the cosmos rang with these primordial notes, till temperatures cooled enough to let photons fly free. The waves froze in place, leaving a faint preference, matter slightly more likely to gather. 150 million parsecs apart than at other separations, billions of years later, those ripples remain. Baryon acoustic oscillations. Stone ring patterns now expanded to grand cosmic scale. Modern surveys such as IBOS and the Dark Energy Spectroscopic Instrument trace millions of galaxies, revealing concentric shells in three-dimensional space. Fly through their data and you swoop past glittering clusters, spaced like tree rings on an unimaginable trunk. Because the original sound horizon is known from cosmic microwave measurements, each ring acts as a standard ruler. Compare its apparent size at different epochs, and you reconstruct how the cosmic lake has stretched. Without relying on supernova flashbulbs or any single method's biases, the verdict aligns. Expansion is not easing. It is quickening. Thus, the universe itself preserved an acoustic fossil, a baseline laid down when no ears yet existed. By reading that frozen music, we confirm the supernova's hint. Some pervasive, unseen influence, dark energy conducts the cosmic symphony, lengthening every bar as the melody unfolds. Starlight travels the cosmos with monk-like discipline, straight ahead at light speed, no complaints. Yet when that steadfast glow reaches our telescopes, its shapes betray a secret. Galaxies that should appear round arrive ever so slightly stretched, as though glimpsed through faintly rippling glass. This is weak gravitational lensing, a subtle warp caused by all the mass, luminous and dark, that the light encountered on its journey. Survey teams like KIDS in Europe and the Dark Energy Survey in Chile have mapped these tiny distortions across a quarter of the sky. They measure not individual arcs, but wholesale shear patterns. Statistical whispers that reveal how quickly cosmic structures grow. If gravity alone reigned, the web of clusters and filaments would tighten with familiar Newtonian vigor. But observations show that growth is languid, as though an unseen counterforce gently loosens the cosmic loom. Dark energy, by accelerating expansion, thins the gravitational glue, letting woven threads relax. Soon, the Vera Rubin Observatory's legacy survey of space and time will chart tens of billions of galaxies, slicing the universe into tomographic shells. Stacked together, these shells will paint a 4D movie of how dark energy dampens the formation of structure. In each frame, the message will persist. The universe is not merely expanding, it is being stretched. And even the paths of ancient photons, the faithful reporters of distant epochs, carry the imprint of that invisible pressure. Pull every atom, ion, and photon from a laboratory chamber, and intuition says nothing remains. Yet quantum field theory insists the vacuum still quivers with zero-point energy. Particles and antiparticles flickering into existence before annihilating in a breath. Tally that jitter with naive mathematics, and you obtain a vacuum energy density a lot larger than what cosmology allows, enough to rip the universe apart in its first heartbeat. Instead, we observe a value so gentle it took billions of years to reveal itself. Einstein introduced the cosmological constant lambda as a mathematical patch. Today, we reinterpret it as the measured energy density of the vacuum, approximately equals 6 times 10 to the power minus 29 grams per cubic centimeter. Why such a small positive number? And why does it begin to dominate cosmic dynamics right now, when stars, galaxies, and curious primates can notice? This cosmic coincidence unsettles theorists. An unguided lottery seems improbably kind. Some propose hidden symmetries that cancel most of the vacuum's fury. Others invoke the multiverse, where countless domains sample different lambda and observers naturally arise, only where acceleration is gentle. Neither answer feels entirely satisfying. The gulf between particle theory and cosmic measurement remains the largest known mismatch in physics. Our most humbling reminder that understanding nothing may be the hardest task of all. As we press on, alternative visions, rolling scalar fields, modified gravity, phantom energies, all vie to explain the paradox. But any successful theory must reckon with this whisper-quiet pressure pervading the void. A pressure ghostly enough to hide for eons, yet insistent enough to steer the destiny of every galaxy we see. What if dark energy is not a constant at all but a restless field? Call it quintessence. Rolling ever so slowly down a shallow potential set in the earliest instance of time. In this picture, the vacuum's pressure is tuned by an equation of state number, W. A cosmological constant fixes it at -1 exactly. Quintessence allows values slightly higher, perhaps -0.95, its influence waxing and waning as the field glides. Some clues already tease this possibility. Subtle tensions between early universe measurements of the cosmic microwave background and late-time supernova surveys hint that dark energy might have contributed a pinch more during the epoch when the first galaxies lit up. But the equation of state can drift lower too. Should W slip beneath -1, theorists speak of phantom energy, pressure so negative it does more than accelerate expansion. It forces it to run away. In that grim arithmetic, the scale factor diverges to infinity in a finite time. The notorious Big Rip. Long before that final cataclysm, clusters would shrug apart. The Milky Way would unspool, planetary orbits would snap like overstretched springs, and in the last trillionths of a second, even nuclei would dissolve into lonely quarks. Current data place W tantalizingly close to the -1 boundary. But uncertainty leaves both serenity and doom on the table. For now, our telescopes keep watch, tracing how the field or constant whispers through the alignment of distant galaxies and the timing of supernova beacons. Hoping to see whether the cosmos is coasting on a gentle hillside or teetering at the edge of an existential cliff. Perhaps the culprit is not a new ingredient, but a flaw in the recipe for gravity. Replace Einstein's elegant tensor with a more Baroque cuisine, say function theories that let spacetime respond non-linearly to curvature, or DGP Bragnold models where gravity leaks into a higher dimension, and cosmic acceleration can emerge with no dark energy fluid at all. Such ideas, however, carry footprints. They alter how quickly structures grow. Galaxies might still drift apart at the observed pace, yet the knots of dark matter binding them would thicken or thin at rates general relativity forbids. To expose those differences, Astronomers measure redshift space distortions, the slight squashing or stretching of galaxy clusters along our line of sight caused by their peculiar motions. Surveys like BOSS, DESI, and soon Euclid chart millions of spectra, extracting a growth factor labeled F sigma 8. Deviations from the CDM prediction act as fingerprints of modified gravity. Meanwhile, peculiar velocity maps, radar guns for entire superclusters. Track flows toward massive attractors, offering an independent check. Even the quiet chirp of a neutron-star merger helps. Standard sirens provide an expansion history free from cosmic distance ladders. Compare that to structure growth, and any mismatch suggests gravity plays by unfamiliar rules on the grandest scales. Theoretical contenders must also evade solar system tests, often invoking chameleon screening extra forces that hide in high-density regions yet emerge between galaxies. Thus, the cosmos serves as a sprawling laboratory, and every new survey tightens constraints around gravity's throat, whether dark energy is substance, geometry, or both. The coming decade will weigh its nature with precision undreamt by the stargazers of 1998. And the verdict will redraw our map of what motion, mass, and emptiness truly mean. At dawn on a July morning, the European Euclid telescope unfolded its sunshield and turned its wide 1.2-meter eye to the dark. Over 6 years, it will chart 2 billion galaxies, sketching a three-dimensional atlas 10 times deeper than any before. Each pinpointed galaxy is a marker on an expanding balloon. Together, they trace how dark energy stretches the rubber from redshift 0.1 to 2, when the universe was one-third its current age. Close behind comes NASA's Nancy Grace Roman Space Telescope, whose infrared camera will catch thousands of supernova light curves in a single stare, tying distant standard candles to Euclid's standard rulers. On the ground, the square-kilometer array will listen for hydrogen's 21-centimeter whisper across cosmic time, converting radio static into a billion voxel movie of large-scale structure, and then an entirely different messenger. When the spaceborne LISA interferometer opens in the 2030s, it will eavesdrop on massive black holes merging at redshifts far beyond any Cepheid or quasar. These standard sirens measure absolute distance because gravity waves carry their own luminosity tags. Compare that yardstick to the redshift of the host galaxy, and you gain another rung on the cosmic distance ladder. Free of astrophysical complexities, together candles, rulers, radio maps, and sirens form a symphonic crosscheck. If they all hum the same accelerating tune, Lambda may keep its crown. Should one instrument hit a discordant note, new physics will beckon. And the silent push, now called dark energy, may reveal its true, perhaps many-voiced name. Dark energy, whatever its essence, is not a distant abstraction. It reaches into every future plan. In 5 billion years, the sun will redden, yet long before then, the cosmic event horizon will have crept so near that only our local group remains within sight. One by one, familiar constellations will melt into infrared ghosts, their light stretched beyond the grasp of human retinae or human sensors. For explorers and engineers, the challenge is practical. A starship launched today toward Andromeda would arrive to find its destination sliding away faster than any engine could chase. Pulsar timing navigation must fold dark energy terms into its algorithms. Laser-ranged beacons must compensate for a metric that subtly inflates while the signal is en route. Even the cadence of future calendars may adapt, marking cosmic years by how much the scale factor grows. Yet ambition is resilient. Concepts for fusion sails, beamed propulsion, and generation arcs already account for the long haul, plotting trajectories against an ever-steepening expansion curve. Some visions turn inward, vast O'Neill cylinders orbiting within the Milky Way's enduring halo, self-contained and content beneath an indigo sky empty of external galaxies. Others imagine data archives messages in bottles launched beyond the horizon now, stressing that some far epoch or parallel cosmos might one day reel them in. In Part 5, Eternal Drift and Human Ambition, we will ride alongside those imaginings. We will trace the probable fates of Voyager, exoplanet probes, and hypothetical light sails, asking how knowledge, culture, and curiosity might thrive in a universe where motion never ceases, but destinations slip forever away. Dark energy has set the ocean in motion. The next question is how we choose to sail it. Look up on a clear winter night, and you witness abundance. Orion's belt, Andromeda's gauzy blur, the faint snow of the Virgo cluster. Yet all this splendor is slowly retreating behind an invisible curtain. In the mathematics of an accelerating cosmos, there exists an event horizon, a radius beyond which light launched today will never, not in infinite time, reach us. At this moment, that boundary lies about 16 billion light-years away. But every second dark energy tightens its grip, inching the horizon inward in moving terms like a slow-closing iris. Meanwhile, gravity knits a final redoubt. The Milky Way and Andromeda are already on a collision course. In 4 billion years, their spiraling dance will forge a single, giant, informally dubbed Milkdromeda, surrounded by a halo of dwarf satellites. Outside that enclave, even the nearest groups will slip past the horizon, their starlight stretched until galaxies fade to ember-red ghosts, then to silence. Future astronomers, peering from within Milkdromeda's glittering core, will see an apparently static universe. No Hubble flow, no cosmic microwave background bright enough to detect, only their own wheeling stars. They will live on an island universe, much as 1920s observers once mistook our galaxy for the whole. The irony is profound. While our grasp of cosmology grows richer, the accessible cosmos itself is shrinking. Inertia continues to fling clusters along their geodesics. But the fabric beneath them swells faster still, erasing destinations from every map. The grand theater endures, yet its audience will someday sit in near darkness, hearing only whispers of an act that once spanned billions of light years. Out beyond the Kuiper Belt, a compact car-sized craft built when disco topped the charts is still coasting outward. Voyager 1 carries a gramophone record of whale calls and back, its plutonium heart whispering 20-watt radio syllables back to Earth. The Deep Space Network's dishes, sensitive enough to hear a fridge light bulb on Saturn, strain to catch those whispers, already a trillion times fainter than the hiss of cosmic microwave static. Sometime around 2036, the plutonium will cool, transmitters will fall silent, and Voyager's voice will fade into the radio night. But the probe's journey has only begun. In 30,000 years, it will pass within 2 light-years of a dim star in Ophiuchus. In 300 million it might cross the outer rim of the Milky Way. Yet even this faithful emissary cannot outrun the expanding stage. Calculate its path on a metric that accelerates, and you find a bittersweet truth. Voyager will never breach the future event horizon. Its inertia is mighty, but the cosmos's swell is mightier still. The probe will asymptotically approach a boundary that itself recedes like a swimmer forever shy of an unreachable shore. Radio waves too languid to propagate. The craft will become electromagnetically invisible. A tiny silent arc, drifting through an ocean whose very fabric outpaces light. Yet for as long as atoms endure, Voyager will bear testament to motion's stubbornness. A relic of a civilization that sensed its cosmic shore receding and, true to human form, launched a bottle anyway, hoping motion itself might carry a message where voices cannot. A starship launched 2 centuries from now will drift through space that does not sit politely still. Each kilometer it travels today will be fractionally longer tomorrow, stretched by dark energy's silent breath. Traditional charts fix constellations, inertial reference frames grow unreliable when the stage itself expands. So, cosmic wayfinders are turning to nature's most precise metronomes. Millisecond pulsars spin hundreds of times each second, their radio pulses as regular as atomic clocks. By triangulating the arrival times of half a dozen such beacons, a spacecraft can pinpoint its position to tens of kilometers anywhere in the Milky Way. Yet expansion tugs even on those timings. Pulse intervals drift redward ever so slightly as spacetime swells. Navigation software must fold in a living term, correcting course with every nanosecond beat. Fast radio bursts promise an even farther-flung compass. These millisecond flashes now erupt daily from galaxies billions of light-years away. Their dispersion measures the amount of ionized gas, and hence distance between emitter and receiver. A future vessel could treat each FRB as a lighthouse flickering on the cosmic shore, updating its coordinates against the shifting metric. All the while, onboard chronometers tick a different tale than cosmic proper time. The universal clock defined by the average motion of galaxies. After centuries in cruise, ship time and cosmic time part ways by minutes than hours. A relativity lesson writ large across interstellar logbooks. In a universe that stretches underfoot, to know where you are demands knowing when you are with equal care. Each correction, a quiet acknowledgement that motion is forever negotiating with geometry's restless sea. Human ingenuity has always answered distance with speed. The Oberth slingshot steals kinetic bounty from giant planets. Solar sails borrow photon momentum. Fusion concepts like Project Daedalus promise 10% light speed dashes to nearby stars. But the accelerating universe moves the goalposts even as we lace our running shoes. Launch a 0.1c craft toward Andromeda today, and after 2 million years the galaxy would greet it barely. Wait 10 billion years and the same delta V cannot catch up. Andromeda's recession surpasses any speed reachable without exotic physics. In the far future, even laser-pushed light sails, clipped close to sea, would find targets receding faster still. Like arrows loosed at a bullseye that sprints away the moment the bowstring twangs. Gravitational assists, once the clever mariners cheat, fade too. As local groups merge into a single elliptic giant, slingshot options dwindle. No Jupiter awaits outbound Voyagers, only the mass we carry and the photons we harness. Generations may learn to ride dark matter wakes, the diffuse halo enveloping Milk Dromeda, skimming potential wells left by annihilation hotspots. Yet each hack confronts the same ledger. Delta V buys distance, but expansion charges compound interest. Infographics of the reachable radius tell a sobering story. At cosmic age 0 gigayears, a 0.1 C drive spans 2 million light-years. By 50 gigayears, dark energy squeezes that bubble to a few 100,000. The universe is turning into a vast treadmill. No matter how hard we sprint, the rubber beneath runs faster. Still, the urge persists. Perhaps propulsion will pivot inward, building O'Neill's cylinders lush with forests, or simulating entire biospheres in quantum processors. Journeys not of kilometers, but of cognition. Motion will endure, but the destinations we chase may become interior realms. Proofs that exploration outlives the maps it redraws. When destinations slip away faster than rockets can chase, the next frontier may be memory itself, carving messages hardy enough to outlast the widening dark. Engineers have already etched libraries onto human hair, thin slivers of sapphire and fused quartz. Their nanoglyphs readable after 14 billion years of cosmic ray peppering. Yet even sapphire will orbit a star, destined to redden and shed its skins. So designers are eyeing colder sanctuaries. One proposal dispatches graphene wafers at Omthin, nearly unbreakable onto sentinel-like orbits far beyond the Kuiper belt. There. Temperatures linger just above absolute zero, and impacts are rarer than supernovae. Each wafer bears genomes, star charts, prime numbers, breadcrumbs for any mind, human or otherwise, that might arise inside Milk Dromeda's future dusk. Other teams think bigger, encoding chronicles and the polarization patterns of single neutrino bursts. Fire a precisely timed train of gigaelectronvolt neutrinos toward a millisecond pulsar, and its magnetosphere will scatter the signal for eons. Only a civilization with neutrino telescopes could decode the staccato prime factor cadence. For still grander ambition, theorists imagine modulating a gravitational wave beacon, nudging a tight pair of white dwarfs so their orbital decay taps out Morse in the fabric of spacetime. An inscription immune to dust, darkness, and even the demise of ordinary matter. Closer to home, a proposed long-time observatory would anchor ultra-precise optical clocks to the moon's far side, recording tick by tick whether dark energy drifts from its measured value. The logs could run for trillions of years, long after Earth's oceans steam away, offering future physicists a baseline older than their stars. In every plan glows the same impulse. If travel falters, let knowledge roam carried by particles and waves that expansion cannot erase. We have watched the horizon tighten, charted starships that can no longer catch their quarry, and designed runic messages meant to outlive suns. Yet through every twist of cosmic fortune, one conviction survives. Motion itself never wanes. Voyager glides on. Photons depart receding galaxies. Virtual particles quiver in quantum dusk. Even when destinations vanish, trajectories persist. Lines etched into a canvas that stretches without bound. Human ambition will adapt. Some descendants may seed entire biospheres inside kilometer-wide cylinders, orbiting the merged core of Milkdromeda. Others might digitize their dreams, surfing processor cycles sustained by captured starlight. Explorers will map inner worlds of thought, mathematics, and art expeditions measured in ideas rather than parsecs. And still, in every turbine spin, in every neural flash, inertia whispers the same refrain. A body, a signal. A pattern keeps to its path unless coaxed aside. As we step into the outro, motion never dies. We will gather the saga's threads, Newton's apple, Mach stars, LIGO trembling mirrors, supernova flashbulbs, and the silent thrust of dark energy. We will ask what it means to live in a universe where absolute rest is myth, where expansion outpaces intent, and where the truest constant is the relentless unfolding of trajectories great and small. So take a breath and feel Earth's spin, our orbit, the galaxy's drift, the cosmic swell beneath it all. The stage will keep expanding, but the dance in every quark and quasar goes on. In the final reflection, we'll celebrate that eternal choreography and set the brush down on this cosmic canvas, knowing the picture itself will never hold still. Pause for a moment wherever you are. Feel the quiet tug of gravity, the breath in your lungs, the faint hum of distant traffic or wind. By every human measure, you are at rest. And yet beneath that hush, Earth is turning faster than the muzzle velocity of a rifle, swinging around the sun at 30 kilometers a second, spiraling with the Milky Way through a halo of dark matter, and surfing an expanding fabric that adds new space between galaxies even as you exhale. Stillness, we discover, is a local rumor, not a cosmic fact. Our journey began with Galileo and a creaking ship's hold, showing that uniform motion leaves no footprint on the experiments we perform inside. Newton chiseled that intuition into law. A body keeps its motion straight and steady, unless a force petitions for change. Mach asked whether distant stars might write that law in the first place. Einstein answered by folding inertia into geometry, letting free-falling apples, orbiting planets, and traveling photons trace geodesics on a pliant canvas of spacetime. We followed that canvas as it stretched, first coasting, then accelerating, driven by a pressure hiding in the vacuum itself. Supernova flashbulbs, acoustic fossils, and faint lensing shears all testified that the universe has pressed the accelerator and will not release it. Ahead of us lies an age, when only our merged local group lights the night. Beyond that, a long blinking out of stars. Motion, however, will persist. Voyager will glide in radio silence. Photons will redshift into whispers. Quantum fields will jitter with irreducible uncertainty. The very notion of absolute rest will remain as mythical as the still center of a hurricane. How, then, do conscious creatures respond? Some will chart new realms of propulsion and navigate an inflating sea. Others will bind memories into sapphire wafers, neutrino pulses, or the creaking orbits of lunar clocks. Perhaps the greatest voyages will unfold inward into art, mathematics, and shared story. Worlds where distance is measured not in light years, but in insight. Whatever course we choose, inertia is our eternal companion. The promise that trajectories once set endure. Even as the cosmic stage expands beyond reckoning, the dance itself will never cease. Motion is the canvas. We are the fleeting brushstrokes. This is Cosmic Canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking. Keep looking up, and never stop wondering.